I'm a software engineer at BuzzFeed, and my focus over the last few years has mostly been on recommender system prediction pipelines, and more recently, also the training infrastructure. But what I want to talk to you today about is kind of a story about our rebuild, our kind of redesign of our related content unit, or our content-based recommender, in other words. Last year, we discovered a need to overhaul the system that we had in place already. The system that we had started to get a bit flaky. It was difficult to work with, and it was hard to diagnose issues that were happening, although it did actually quite well for users. And so we embarked on a project to see if we could reduce the overall complexity of the system. A goal was not to increase KPIs. We just wanted to see, design a system that was much more simple to maintain and, projecting into the future, allow us to do things that we wanted to do more easily. And, this has come out of actually the internal meetings that we had to arrive at a decision for the system. And there's like a neat kind of intersection between designing a system like this and some of the stuff that Barry Schwartz talks about in his book, The Paradox of Choice. So there's a lot of interesting things about this book. I don't want to talk about all of them, but it kind of switches things into buying and selling, right? I got interested in this primarily because of the psychology and psychological aspects of recommender systems and what they might be. And the lesson I learned was actually that was much kind of less interesting than some of the human factors that came up when designing systems. But there's one thing, just to briefly touch on this, I don't want to talk about this too much, but if you read about recommender systems, you'll occasionally come across this experiment. If you're researching how many recommendations should I present to the user, this was carried out in 2000. People would go into a shop and they would see one of these two variants. I've represented jam jars with honeypots, but they would see lots of different jams, right? They'd have a choice of 24 versus 6. And the experiment was to see which they engaged with more, what people went up to, what they engaged with, and what they actually ended up purchasing. And the results were quite interesting in that 40% actually approached this, right, versus 6% on 30% on the 6 jam jars. But which isn't maybe too surprising. This is maybe a little bit more attractive to people. But in terms of sales, this actually achieved 31% of sales compared to this. So showing less kind of can drive better engagement. So this is kind of from the selling perspective, and we might take from this that we should sometimes try showing less recommendations. That might do better. But as the user who is interacting with this, that's kind of actually a more interesting angle on this, I think. So one of the things in the paradox of choice is there's this kind of fallacy that the more choice we have, the more freedom we have, and then the more freedom we have, the greater our welfare, right? And so they're saying that choice is good. And this is an example that Barry Schwartz gives, that you go into a supermarket, you look at salad dressing, there's just a stupid amount, right? How can you possibly arrive at a decision? And there's lots of other arguments. He has a TED talk on it. It's really worth watching, actually. I don't want to talk about it too much, but when we see such astounding amount of choice, it leads to decision fatigue, or really a paralysis of choice, right? And then kind of worse than that, if we make a decision, there's a chance we might regret it. And that's a real human factor, right? There's a real human side of decision making. And this also parallels well with designing a system, especially a system that involves machine learning components. And so another aspect is for people in this kind of industry, we have to also justify our choices that we make. And that's it takes a lot of time. And the more choices that we have, the more justification we have to do, and it's a very time-consuming process. But what I really want to do is talk about how this pertains to building a content recommender system, and also kind of the differences between me, as an engineer, versus the data science or machine learning practitioner decisions that have to be made, because they're really different, and surprisingly so. So let's build a system to recommend similar content We need an API, of course. We need somewhere maybe to store recommendations or to store some kind of information. We need probably some ML for training prediction, potentially. And we need luck, right? A healthy dose of it. So the first things first, I'm an engineer, I need to build an API. At BuzzFeed, we had 3 choices, language-wise, Python, Node, and Go. And our existing recommender got about 500 requests per second. And so, we would save ourselves potential headaches later on by just switching to Go. So that's initially what we did. And then the next question is kind of, what does this API do? What does it interact with? And so there's kind of 3 major choices. One is a key value store. So this is where someone gives us an ID and says, give me related stuff. We will look in some key value store with this ID and hope that someone has put recommendations there. If they have, we'll serve them. It's great, very simple. Nearest neighbor index is similar, except we allow ourselves to do a little bit of compute, right? We don't have pre-computed recommendations, but we have some index of embeddings, which are probably vectors of numbers that represent our content. And that's interesting for lots of reasons. It's kind of a little bit more alive. You can do more dynamic things with it. And then there's a model-based approach where you immediately hit a prediction function on something. Maybe you've trained some multi-class classification model, or there's lots of different opportunities to do stuff there. But our content changes rapidly. We have a lot of new content every day. Community users contribute to us. So the retrain frequency would be kind of cost prohibitive. So we can kind of rule that out immediately. So we're left with 2 options now. And so let's take a look at the key value store. So we need someone to come and put stuff into it, put recommendations into it. So we needed some triggering process. So if we read this right to left, some triggering process, we are going to do it in batch or stream. When we do batch, we're probably going to use Airflow or some cron job on some EC2 instance. Or streaming, we're going to use cloud functions, which are interesting because they can also trigger Airflow jobs. Or an NSQ reader, which is some open source Q reader that we use. And immediately we can hit decisions on this. We use Airflow. Typically, that's kind of where we're trying to move to. It seems like a cleaner thing to do. And we have a lot of experience with NSQ, so we would probably do that. So those things would trigger either training or kind of utilization of an embedding model. And I'll come back to this embedding model, but typically, and what we're talking about is some model that converts text into a vector. And then when we run that through some nearest neighbors thing to get k nearest neighbors, we hope that they share some similarity, maybe semantically or entity-wise. And so we'll come back to these. But we pipe that through to the nearest neighbor index. That gives us, maybe we'll store 20, and then we can store those in our key value store. And we only use Redis for key value stores. So immediately another decision is made. The nearest neighbor index is very similar. This is kind of a subset of what we just saw, right? We still have the same triggering process, an embedding model. Nearest neighbor index now, maybe it was a library before, but now it's more of an application. But we get this power when we use the nearest neighbor index, which is we can fetch embeddings on demand. If they're missing, we can say, hey, give me them. And that can really reduce our time between publish and recommendations being available to serving. And for our content, that's important because after a post is published, that's when it tends to be most popular. And so, right, so what we've covered is really the engineering stuff, the stuff that I work on. And it's quite nice. We've basically been able to make decisions. It's fairly binary. We're fairly confident in the outcome of what it will be. But now we have to move on to those other things, the embeddings, right? And the nearest neighbor index. And those are full of uncertainty, right? So let's take a look at those. It's a little bit different, right? These decisions are much more difficult. So picking an embedding model, here are some. These are like libraries or papers or some pre-built models. And how many are there? Effectively, there's infinite number of these things, right? How can you possibly choose from an infinite number of uncertain things? Very difficult thing, and it makes me glad I'm an engineer, right? I don't have to make these choices. But it's really daunting, right? And then we have to provide training data for that. So where do we get our text from? Do we use our own data from articles or maybe from our videos? Do we use Wikipedia, something called Kaggle? Do we scrape Reddit? And that seems to be popular at the moment. Again, like the choices here are astoundingly large, practically infinite for all intensive purpose. And then we need to decide how to tokenize, lemmatize, pre-process, what stop words to remove, how do we handle different languages? And then, only then do we get to actually train something, which can be a very cost prohibitive process for text-based models. Get a little bit of respite with the similarity metrics, the distance functions that we want to use. This isn't an exhaustive list, but there aren't too many traditionally used, but we still need some engine for which to run these things. So we need a nearest neighbor index, right? And there's a lot to choose from here as well. But actually, this is kind of finite, right? There's not too many more. These are kind of the most popular that you would traditionally use. Some of these are libraries. Some of these are not maybe suitable for high-scale serving. And so we can kind of narrow it down a little bit. And we have this respite that brute force is always an option here, right? That's nice. Maybe something that we can leverage. So, okay, let's take a little break. That for me is like the scary stuff, right? That decision, I don't know how anyone could possibly make it. And maybe you don't have to make it. Maybe you have just enormous resource. You can just rely on decision theory and massive scale computers to try and work it out for you. But we're not that lucky, right? We have constraints. We have to work out what to pick from this kind of set of things. And that's tough, right? So it gets a little bit scary. This is just everything put together. I want to talk about what we did at BuzzFeed with what constraints could we possibly apply to make this work out for us. And what we kind of arrived on was, maybe we don't need to train our own embedding model, right? And if we didn't train our own embedding model, then maybe we don't need infrastructure to trigger. We don't need to choose training data. We still need an embedding model, but maybe there's some that already exist for us. We have these pre-trained models. So that's what we did. We decided, let's use TensorFlow Hub. They've had millions of dollars of compute resource and research poured into them. And so it'd be kind of naive to think that we could immediately do better than these things, right? And there's also side effects to using these things, which is quite nice. So if we pick universal sentence encoder, that is built to work with cosine distance, right? So that decision has been made for us. So we can kind of bring these things down. And then maybe we can rely on brute force as well. And actually we can, right? Our embedding space is small enough and our kind of candidate list of documents is small enough that we can compute this stuff in tens of milliseconds. And we can also cache that for a short duration, right? So brute force is viable, and the universal sentence encoder is kind of what we landed on. So we actually, worked on this over a year ago. TensorFlow Hub had much more finite list of things to choose from back then. And universal sentence encoder seemed like a good option because it was very easy to just pick another TensorFlow Hub embedding model, right? There's low-hanging fruit in these things. So there's no real risk in just settling on one of these things initially because we're able to try them all out later on, which is a really powerful thing. And then we can simplify this even further. Maybe actually we don't need Redis anymore. Let's just compute nearest neighbors with brute force, cosine distance, as close to the user as possible. And this is really a simple architecture. This is kind of what we landed on. And yeah, I think it's worked out pretty well. It's interesting that we didn't set out to improve click-through rate, but we have. We've managed to gain a little bit through doing this exercise over our word-to-vec model before. Cost-wise, it runs for hundreds of dollars a month compared to thousands before. It's much, much cheaper. So our return on our investment is, very, very, very good. And but it's not all like sunshine and roses because having these black box models has really meant we have suffered some issues. When Disney Plus was announced, the token Disney Plus caused all of our recommendations to be served as Japanese recommendations, very unusual. So we had to actually kind of wrap these models in our own text pre-processing because they have their own built-in, right? We just have to add a little layer above that. But generally, it's worked out actually pretty good. And through applying really a lot of constraint, it's kind of boring what this looks like now. But this constraint has just allowed us to claim low-hanging fruit and avoid regret. This is a system that we are very confident will be quite reliable, resilient, and it's cost to run. It's cheap to run. And so, those are all very important human factors to consider. And so just to close off a bit, some quotes from this book. Learning to choose is hard. Learning to choose is harder, and learning to choose well in a world of unlimited possibilities is harder still, perhaps too hard. And when these options you have are riddled with uncertainty, because this is machine learning, it's basically impossible. Yeah. Focus on what makes you happy and do what gives meaning to your life. So this kind of draws back to the human factor, right? I don't want to spend my time worrying about these decisions. And, BuzzFeed as a whole has benefited from this as well, because I get to focus time on other things. But also, I don't have regret, right? And that is a real powerful thing. To regret something you've built, to think, oh, maybe I should have chosen that other thing, that has really serious personal consequences, which we can avoid. And finally, choose less and feel better. This is obviously easier said than done in this field especially. But yeah. This whole project has made me have a lot of empathy for machine learning practitioners, the people who have to make these decisions, right? I don't understand it, but if you need a hug, I'm here for you. And join BuzzFeed, we're hiring. If you're interested in these sorts of problems, then we're doing a lot with them at the moment. So, thank you.
So yeah, we have time for a couple of questions. Keep up with the agenda. Questions? I have a question as well.
Go first. Thanks for the talk. My question, I'm quite surprised that you got away with brute force for your nearest neighbor calculations. What size of corpus were you working with?
So we can get away with about 200,000 documents in the corpus.
Using brute force?
Yeah, so if you use, so our embedding lengths are 512, right? And if you use SIMD vector instructions, then you can, so there's a little bit of assembly, right? But it still is brute force. We're not approximating anything. So if you just allow the computers, they have very good instruction sets for these large vector calculations, then you can divide that time it would normally take by about 32 at the moment.
But so you managed to get around the quadratic complexity. If you've got a 200K corpus, then you're basically comparing 200 times 200 on.
So when a request comes in, we're comparing for one ID.
I see. So it's like a streaming process. Okay, I got you.
Yeah, so we avoid that whole offline process where we would have to do the quadratic lookup. Yeah.
Okay, thanks.
Thanks for the talk. It was super interesting. You talk about that you chose a pre-trained model to remove complexity, which is probably a very good move. Have you built in ability to train on top of it for the future? And how much do you think context dependent things, those things that mostly appear on BuzzFeed only, that won't be in these pre-trained corpuses, do you have a feel for how much that would affect your recommendations?
Yeah, so I'm not super sure how it would work. I know people use these embeddings and then they train classifiers and such with them. I'm not sure how you extend it to do better embeddings, personally, but if we could do that, then I'm sure we would. We definitely have a different language than Wikipedia, right? And so there would be some benefit to leveraging that if we could, for sure.
Hiya, great talk. I was wondering if you're working on adding any additional information to what recommendation you eventually figure out beyond just the corpus. You mentioned the importance of the recency of published to BuzzFeed articles. Is there work going on to add that and other information into the thing that's ultimately recommended?
Right. We've actually tried that. We tried re-ranking. So we have a hybrid recommender where these kind of algorithms apply a candidate list, and then we can apply re-ranking on top of it. So we tried recency, just full re-ranking with recency, and it didn't actually benefit. Like there's no change in KPIs, which was surprising because internally people were requesting that change, like our editors and so on. But yeah, there was no actual change in user metric.
Interesting. Thanks very much.
Let's do one more question.
Yep, over here.
This is more of an engineering question. At what points in the stack do you cache these recommendations, and how long are they, roughly, how long are they cached for?
So, in this case, we don't cache, right? Embeddings are stored and computed in real time. We can cache for sure. We found that we don't need to. We don't use a CDN because we want to ensemble other kinds of things into this potentially. It's kind of like a very general purpose recommendation API that we have that handles the hybrid side of things, and so we don't CDN cache. And we try to do as little caching as possible, just to allow ourselves kind of flexibility to merge things together.
Any other questions? Yep, okay, so final one. Just while I'm giving you the mic, if anybody wants to tweet, then the hashtag is RecSysLDN.
Hey, thanks for the talk. I think my question is related to the two folks asked before. So you're basically using TensorHub and use pre-trained models. So what if you want image embeddings or video embeddings, and then how are you going to do that? And then how about the real-time one? Do you not want to add the real-time recommendation together with your previous index?
What do you mean with the previous index?
Oh, so your index, basically your batch processed index with real-time. Maybe you want some real-time element in your recommendation?
So the embeddings appear in real time, right? And they're added to the index in real time, and they'll be available pretty soon after they're published. So that part is covered. Do you mean real time in terms of ranking or?
Yeah, it could be anything that you have to handle real time. It could be just embedding, but it could be just signals. Maybe there's something suddenly got the heat and you want to pop into that recommendation consideration.
Right. Yeah, the recommendations tend to be there when we need them to be, like quite quickly, for our text articles, right? So you mentioned video embeddings and image embeddings. We don't actually do that. We have a project going on to improve how our images are described, and that text becomes part of our text for the embeddings that are generated. Videos, we actually leverage YouTube a lot for those recommendations. They kind of do it for us, which is nice. Yeah, maybe we can talk after. Yeah.
So let's thank you to the speaker.